Thank you very much for joining us. The webinar today is going to be on mastering tunnel design and analysis with RS2. I'm Ali Reza. I'm Director of Research at Rock Science. And today we have our special co-host guest, Gabriela. She brings a wealth of knowledge and expertise on the subject. She is a dear friend to all of us at Rock Science. And we are very pleased and delighted that she accepted the invitation to join us for this presentation. I will leave it to her to introduce herself and the company later on during the presentation. I will just do the brief intro at the beginning. So, about Rock Science. We are a world leader in developing innovative 2D and 3D software for civil, mining, and geotechnical engineering applications. We are dedicated to delivering industry-leading software program, exceptional customer service, and unparalleled technical expertise that the engineers can rely on. 25 years ago, 30 years ago, the team was 4 people. Now we have grown to a team of 80 with 4 offices around the globe with representatives everywhere. And we are trying hard to build those geotechnical tools that are used by our users, more than 10,000 across the globe. These are the software suites that we have. We provide comprehensive solutions to different problems that geotechnical, mining, and civil practitioners might be faced. And the reason for that is that you might deal with different kind of problems. So different methodology, different mathematics formulation will be applied to them. So you have different tools to apply to different problems. Or you would like to apply different methodologies, mathematics formulation tools on the same problem. In that case, you can run different tools, get a more comprehensive understanding on the problem that you are analyzing and dealing. On top of that, we have the ecosystem that we have, the integration between the tools that we have. Again, let's say you are looking at the slope stability analysis. So you can apply multiple tools, like RS2, for example, different methodology on the same problem, and you will cross verification between these results that you are getting. Or you have a complex problem that you're dealing with, then you might need to apply multiple of these tools to handle different portion of this problem, different aspects of the problem, and you have, again, a comprehensive solution that you have for that specific problem. For the agenda for this presentation, I will present a quick feature review. The simple part is mine. And we have 2 major parts for the general aspects of tunnel design and finite element analysis, RS2 workflow, and also a case study that Gabriel will take care of. So I'll start with the easy part, then I will pass the presentation to Gabriel. So what I will talk about is simulating 3D effects in 2D tunnel analysis. So if you're looking at the image here, so for tunneling, we have a lot of sequence of excavation, support installation, different regions of tunnel will be excavated in different sequence. It's a pretty complex problem. One thing that is a key is this profile of deformation that we have. So this one shows the pattern of radial deformation in roof and floor of an advancing tunnel. So if this is, for example, the same thing in cross-section, this is your tunnel advancement. This is the face of excavation. This is the tunnel displacement behind it. These are the excavated area. And at some distance from the tunnel face, you will have the supports coming in. So the distance that we have between the tunnel face and the support system, the lining system, is where you have might have different issues with displacement and stability. Now, the key question is that, what is that excavation closure or stress relaxation at the time of support installation? So that displacement we are dealing here. And how can we predict that, simulate that in 2D? If you want to go for 3D analysis, we have 3D tools, RS3 and Diana. You can do a fully 3D analysis that can simulate the entire sequence of ground excavation and the time installation of various support system accurately, reflecting what is actually happening in the field. And you have that construction sequence exactly implemented in your 3D analysis. If you want to do that in 2D, there are 2 approaches that I will introduce here. One is core softening, the other one is induced slope. These are the approaches that we have in RS2. The core softening approach simulates the stress distribution around an excavation by replacing the excavated zone with the lowest stiffness elastic material. And this core, that is the software code, deforms under stresses to that is stresses that are coming from the surrounding ground. As this system deforms, the stresses absorbed from the surrounding ground to the core, and that actually mimics the stress relaxation in the surrounding ground. The other option is induced load. The induced load option in RS2 replaces the effect of the excavated material by applying an equivalent load on the excavation boundary based on that pre-existing stresses. And when this load is applied and you're applying a factor to it, which is less than 1, for example, with that, you're actually effectively simulating that stress relaxation. So that stress relaxation, the factor is going to be that 1 minus the load factor that you're applying to that load. How do this work in practice, in action? I'll show you this example in 3D. So this is a tunnel, for example. We are looking at the sequence of excavation. Let me click through a couple of stages. You can see there are different sections of it being excavated, and there are multiple staging and all that happening around it. When I want to do that in 2D, so this is the geometry that I have. We have that course opening, for example, liner coming in, another course opening, liner coming in, different region course opening, different region line, and gradually you're simulating the same effect of 3D with that stress relaxation, and you time when your support are coming in to get that full excavation. There you go. Presentation. Now, so how do this look? What I'm showing you here is the same simulation. This is the stress relaxation at the first strip. We are looking at vertical displacement in 3D, 2D with induced load option, and course opening. And for the induced load option, you can see that I'm actually applying 70% stress relaxation. Now, look at the pattern of deformation, vertical deformation between all these 3 cases. I will click through stages. You can see how well these 2D simulation are actually mimicking the same effect and deformation that we see in 3D analysis. If one support installation, gives to stress relaxation, support installation, have stress relaxation for bench 1, support installation there, stress relaxation for bench 2. Bench 2 is fully excavated, you have the support in. What pillar is experiencing that stress relaxation, and this is the full excavated region also support. As you saw between all these 3 scenarios that I'm showing you, the pattern, the values, and all that, they are very much in agreement. So for these kind of scenarios, you can actually effectively simulate that 3D effect in 2D analysis. Now, when we are doing that, a very important question is that what is the excavation closure or stress relaxation at the time of support installation? That 70% relaxation that I applied, or that modulus that I'm defining for that core, for the course opening, what are those values? How do I get those values correct? So that includes 2 steps analysis. In step 1, what we should do, we determine the closure based on Blachopoulos and Dietrich method. Based on this graph and all the analysis that they have done, they have provided this very nicely structured chart that you can use to, based on the tunnel radius, plastic zone radius at the fully excavated region, distance from the tunnel face to support installation, and maximum closure at fully excavated section, you can find what will be your closure at the time of installation of the support. Having that, you can go in the second step. You determine the stress relaxation to give you that closure. So that stress relaxation is going to be in terms of modulus of that course opening, or that induced load factor that you're applying to match that closure that you're seeing from that chart. To do that, you run a simulation and adjust that stress relaxation factor, which is, for example, in this case, that modulus of the core. It is adjusted through that simulation, and you find that characteristic curve. So this is that closure that you're calculating in that 2D simulation. If you match this closure with the one that you find here, it's going to give you what is the value for that modulus of core that you need to apply to the system? Or what is that factor that you need to apply to that induced load factor? So based on that, you can actually mimic a lot of those 3D effects in a 2D analysis, and that's how RS2 can be very valuable in tunnel design and analysis. With that, I'll pass the presentation to Gabriela.
Hello, everyone. I'm Gabriela Piazzetta. I'm thrilled to be here today to talk about tunnel design using RS2. So before we dive in, I will briefly introduce myself. I'm a geologist with over a decade of experience in both geological and geotechnical projects. My expertise lies in geotechnics, tunneling, and numerical modeling. I have the privilege of working with RS2 in significant projects like CJ Santiago in Ecuador, lines 2, 4, and 6 with the São Paulo Metro and Porto Metro in Portugal. Currently, I'm a tunnel design engineer at CJC Engineering Projects. We are a company specialized in tunnel engineering with a global presence. Our portfolio includes over 130 metro stations and more than 400 kilometers of tunnels worldwide. All this experience gives us a unique perspective on the challenges and opportunities in tunnel design. So having the support of advanced tools like RS2 is essential for us to develop high quality and reliable projects. I want to extend a special thank you to Rock Science and Alireza for hosting this website and the invitation, and to CJC for allowing me to share insights from our projects. So today I will explore how RS2 helps us design better tunnels by tackling real-world problems. So we'll start with general aspects of tunnel design, FEM analysis, and RS2 workflow, and then we'll move to a case of study where we will investigate unloading modulus and residual parameters for back analysis and groundwater behavior modeling and interaction between tunnels and foundations. So I hope you enjoy. So effective tunnel design begins well before we open any software. And it's critical to understand the preliminary considerations of any tunnel project. So these considerations guide our modeling approach and ensure we are addressing real-world challenges effectively. So we can group these factors into 3 main areas. So the geometry includes tunnel size, tunnel shape, stages, and excavation sequence. These parameters directly dictate how we will represent the tunnel within RS2. The ground conditions encompass the soil and rock properties, groundwater levels, and permeability. So accurate data here is crucial for simulating realistic ground behavior in RS2. We specifically need to understand how water will interact with the tunnel and how we want to model it. And the external influences covers existing utilities or infrastructures, project stage, and timelines, budget constraints, because these factors influence the level of detail and complexity we can achieve in our RS2 model. So by carefully considering these factors, we can select appropriate material properties, boundary conditions, and analysis methods in RS2. And it helps us anticipate potential issues, ensure safety, and recognize the limitations of our model. Allow us to use RS2 more effectively and optimize the design and solve real-world problems. So why RS2 is suitable for tunnel design? For internal excavation causes stress changes in the ground. And these stresses redistribute, creating strands around the opening and loads on the tunnel support. As designers, we need to ensure excavation stability, control ground settlements, manage stress on the linings, and minimize impact on nearby buildings. So traditional methods like shell spring approach don't capture the complex ground behavior, often oversimplify these interactions, and limit equilibrium limit equilibrium methods don't provide this stress strain analysis. So that's why we use RS2. It's a fan-based software that provides the best solution for this kind of analysis. It gives us the stress and strain in the ground and stresses on support, and it can handle complex geometries and let us simulate each step of excavation. It also enables us to model nearby buildings, foundations, and groundwater. So RS2 solves all of these complex problems by dividing the problem into a finite element mesh, which can generate automatically and with great accuracy within the software. Let's walk through the typical workflow for tunnel modeling in RS2. So we first start by importing the tunnel geometry and soil layers from CAD into RS2. Alternatively, we can design the tunnel directly within the software using the tunnel designer tool, and we can build the soil stratigraphy using the borehole tool. Next, we define the soil materials, specifying their stiffness and strength properties, and selecting appropriate constitutive models. In many cases, we use the Markulan model, which requires cohesion, friction angle, and dilatancy. We also define the hydraulic parameters to account for the groundwater effects. After that, we set up the different stages of the model. These stages typically represent the sequential excavation and construction steps, allowing us to simulate the tunnel's development over time. Then we define the initial earth pressure coefficient. We would typically use a gravity-based approach for shallow tunnels or a constant value for deep tunnels. This represents the initial stress state of the ground before excavation. We also apply any relevant surface loads, such as traffic or building loads, that might affect the tunnel. A critical step for tunnel design in 2D is define the stress release steps to simulate the reduction in the ground stresses as the excavation proceeds, which was just covered by Alireza in the previous presentation. The next stage is the generating of finite element mesh, which divides the model into small, manageable elements for calculation. We always need to check the mesh quality to ensure that all elements have a manageable geometry. And we can automatically do this mesh and check the quality within RS2. And we finally define and insert the tunnel lining and apply the groundwater boundary conditions and define the model restraints. So these are the most common steps for tunnel designing. So now all of this might seem pretty theoretical, but things get complex when we apply it to real-world projects. So I want to share a case study to illustrate how RS2 can be used to address real-world challenges. So this is a metro tunnel constructed using an NITM method in a challenging residual soil of São Paulo. I'm not going to walk you through every single step of the modeling process. You can find detailed tutorials on basic tunnel modeling in RS2 in the rock science documentation. Also remember that every tunnel project is unique, and the modeling approach needs to be tailored to specific project assumptions and conditions. So instead, I want to show you how we use some RS2 advanced tools to overcome specific challenges in this project. So the project was divided into segments based on their main challenge. One of the main challenges here for the entire tunnel was the need to predict settlements with high precision. So the tunnel alignment passes through areas with both shallow and deep building foundations, meaning that any ground movement could have significant consequence for the stability of the structures. Also, because we're working with residual soils, the interaction with groundwater was crucial. The soils can sometimes behave as collapsive soils, and they also exhibit time-dependent deformation effects. So we had to model groundwater conditions as realistic as possible. For the first section, we obtain observed displacement and groundwater flow rates, and we use them in a back analysis. This means that we compare observed deformations and settlements against model predictions to adjust the soil parameters for the subsequent excavation. We're gonna go over some details of how to do the back analysis by using soil parameters and the options we have in RS2 to model groundwater behavior. In other sections of this tunnel, we are excavating under shallow and deep foundations, so we'll briefly touch on this while showing some results. So this is the geological context. We counter a soil profile that's typical of residual soil formations. This profile usually consists of a mature soil layer, which behaves largely as a homogeneous material. Below that, we find a younger residual soil layer that might still contains preserved rock structures. And beneath this, we have saprolite, which also preserves rock structures, and then it transitions into weathered and finally intact rock layers. The tunnel excavation primarily occurred within the residual soil and saprolite layers. You can see here in the picture. And in this type of project, soil parameters and constitutive models are generally defined based on SPT data and the prior experience of design engineers. So typically we use Mark-Coulomb model for the soil layers, while the Hook-and-Brown model is more appropriate for the rock. So starting with the back analysis. Back analysis is a powerful technique we use to refine our numerical models. It involves adjusting the soil parameters in our model until it exactly reproduces the behavior we've observed in the field. So think of it as an iterative process. So we vary the unknown parameters, run the model, compare the results to reality, and then repeat until we get a good match. In this process, we can modify various aspects of the soil model, including the constitutive model itself, the strength parameters, and the stiffness parameters. The decision of which parameter to adjust and the range of values to consider should be based on our experience and any available lab results. It's important to exercise good judgment here to ensure that the parameters remain realistic and grounded in factual data. When we are dealing with underground design in residual soils, two of these soil parameters become particularly relevant for correlating with soil settlement: the unloading modulus and the residual strain parameters. The unloading modulus is a key parameter for underground design because we are primarily dealing with soil that's being unloaded and as we excavate the tunnel. So modeling the soil with different Young's modulus values for loading and unloading behavior provides a much more realistic representation of how the soil actually responds. And finally, residual soils are known to exhibit residual strength values that are lower than their peak strength. This is often due to the loss of cementation within the soil during loading. Therefore, accurately capturing these different strength parameters is crucial for a realistic model. Here's an example of how changing the unloading models and the residual cohesion can impact the settlement curve. In red, in the picture, we have the monitored points from the field. In yellow, we have the results from our initial analysis, without considering unloading and residual parameters. And as we adjust the values of unloading modulus and residual cohesion based on lab tests and reference values, we can achieve a much more realistic settlement curve that better matches our monitored data. These parameters can be easily implemented in RS2 software in the materials property menu. And I'm going to open RS2 and walk you through how to implement these changes in the software. So let me open here. Okay. So here we are in RS2. I have one of the models done for this tunnel. We have the tunnel geometry and soil layers already defined here. And so let's look how to define the unloading values for young modulus. So we go here in the define material properties. We have here the materials defined. And we need to go here in the stiffness tab for isotropic material. You can just check this box here, and you are able to tap the value for unloading modulus here. And keep in mind that this option is only enabled if your failure criterion is set to Moore-Coulomb, Hooken-Brown, Druckenprager, and generalized Hooken-Brown. So you can fill the value here, and you can define the criteria for the unloading condition. So specifying whether it will be determined by a change in the mean or in the deviatoric stress. So the value for the unloading modulus will then be used in the analysis whenever the material is subjected to an unloading change based on this condition that you choose here. So keep in mind that the unloading condition is not the same as the residual modulus, which is another option here. And also remember that applying the unloaded condition will add some complexity to the model. So you may experience some need for more computation. And you can define it only for the materials you want. If you don't want to apply the unloaded condition for a specific material, you can just uncheck the box. And you can also apply different values for different materials. So next, we'll take a look on how to define residual strain parameters. So we move to the strain tab here. So RS2 allows us to input both peak and residual values for cohesion and friction angle if you're using Moore-Coulomb criteria. This means that after the initial yielding of material, the strength instantly drops from its peak state to residual state. If the residual values are the same as the peak values, the behavior is elasto-perfect plastic. So you can change all the parameters, or you can change just the cohesion or just the friction angle. Remember that you need to be working with a plastic material. If you go here in the elastic, you won't have the options to fill the residual parameters. So you need to be in plastic, and you can choose whatever you want to change. So depending the values you enter for these parameters, they will significantly influence the settlement results. So it's important to choose carefully them specific based on our site specific data and engineering judgment. To talk a little bit about groundwater, RS2 offers 3 methods for groundwater analysis: the static water, the steady state, and the transient. You need to set the groundwater here in the project settings. Okay, I'm gonna open the project settings, and you have the option for groundwater here, and you need to choose the method here. And you also need to define the units that will be used for the flow rates. So you can go back here in units. You can choose the time units and the permeability units. If you choose the static mode, you will define the geometry of a piezo line or a grid to represent the pore pressure conditions. And if you're working with steady state or transient analysis, RS2 computes a finite element seepage analysis to determine pore pressure distribution based on groundwater boundary conditions. So we're going to keep a steady state a method here. And then after you generate your mesh, you can go to groundwater. And I'm going to go to this stage. And you can choose and set the boundary conditions. Remember that, you need to generate the mesh first. Defining the groundwater boundary conditions in tunnel design can be tricky. We have so many geological complexities and drainage devices make it hard to accurately determine the pore pressure distribution around the tunnel. So we typically treat the excavation line as a free draining phase, and the drainage devices and the external water conditions vary based on the proposal hydrogeological model. And we have published a paper last year discussing the influence of time on defining the radius influence of drainage. We'll leave the link at the end of presentation. For this example here, we had both the location and the flow rate for the deep horizontal drains. So we were able to use these specific boundary conditions called nodal flow rate, where we can input the data for the flow rate value here. And for drainage, we need to input these values as negative values, and you can apply to boundary nodes. I will just apply here to one boundary node and apply it here. So we can just apply and run the models, and you're considering that you're extracting, the water here is being taken out of the model. And with this, we can compare the model drawn down to piezometer data to verify if this approach is realistic or not. So close here. So I'm gonna open some results here. So here on the right, we have a model with no residual parameters and no unloading modulus. So we can see the settlement and the yielding here. And on the left. And on the right, we have a model with unloading modulus and residual parameters with a lower in the cohesion. So we can see that we have, because we changed the residual parameters, we have an increase in the yielding. But as we work with the unloading modulus, we have a decrease on the settlements. So you can see here is with 45 millimeters, you have here for 31 millimeters. So this is very nice when you need to adjust your settlement. And you also have here the groundwater line. So you can easily check if with your data from piezometers, you can check if this is matching to the field observations. So I'm gonna move back to the slides and go to this one. So as we work with tunnels in urban environment, we are already very concerned about settlements in the buildings, and we need to be super careful about their foundations. So I won't cover this topic in detail because it would take a full webinar just on this. I will just show how we can model foundations in a few different ways in RS2. So the simplest way is by using a simple load. You just add the building's weight as a load on the ground surface. This is good for quick estimates, but it assumes the building moves exactly like the soil. So we usually do this for buildings with shallow foundations or for the first assessment of expected damage. A variation of the simple load is the beam model developed by Burland, where you model the building as a thick beam. This takes into account the building's stiffness, so it can be helpful in a more detailed definition of the associated damage. Or you can explicitly model the foundation, like the piles or footings. We usually do this for buildings with deep foundations. In RS2, you can use the pile tool to define the rigid element and its interface and the connection with any horizontal structure. So on the left, we have an example of shallow foundation where we apply the load at the level of the footings of the building on the surface of the model. And on the right, we have an example where the interaction with the building and the tunnel are significant. So we had to model the piles in detail. This let us simulate how the tunnel interacts with the piles, and we could even verify the structural integrity of the piles after the tunnel excavation. So we've seen today RS2 is a powerful platform that helps us in every stage of tunnel design, from planning to addressing real-world challenges. With RS2, we can simply optimize design, simulating ground behavior for efficient and cost-effective design. We can address complex challenges and overcome difficult soil conditions, structure interactions, and groundwater issues. We can analyze failure modes and optimize support systems for safe and reliable tunnels. And we can use back analysis to improve predictions based on real-world data. Also, Rock Science has a powerful AI tool called RS Insight. It's available through the Rock portal. It's an AI-based tool where you can ask questions about rock science softwares and the concepts behind the tool. And it's a great resource to use if you have any doubts on how to model things. So,
thank you very much, Gabriela. Great presentation. I enjoyed it. If anybody has a question, you can type in that question box. I have listed some of them here. I will share it. Gabriela, you take some, I'll take some. I think this should be good for you if you can take care of this. There are lots of challenges for groundwater and groundwater boundary condition. I have seen a lot of your models coming as tech support. I've seen how creative you can be with those. Give us some of your strategies to overcome these challenges that you see for groundwater.
Yes, so you're right. Yeah, definitely groundwater boundary condition, it's like quite challenging. One of the main challenges we have is determining the drown down influence radius. So usually we often start with the C-sharp formula for initial estimation, but sometimes the values aren't quite right when we are talking about 2D and urban tunnels. So what we have done last year, we published a paper. Let me see. I think I have the... Are you still seeing my screen?
Yes.
Yes. Okay. I think I have it here. So we published this paper. So what we do is using RS2 to run a series of transient analysis. So we could establish a relationship between the time and the influence radius of drown down for different permeabilities. and we compare this to C-shared values results. So depending on this and based on this chart, you can sometimes account for the time in defining these drawn down regions. So it's very useful for 2D modeling. Thank you for hosting this webinar. For me, it's a pleasure to talk about this subject. And if you all need any support on this, feel free to contact me.
Thank you very much. It was a great pleasure having you on the presentation. Thank you for your help. We appreciate that. Thank you, everybody, for joining us. The rest of the question, as I promised, we will get back to you via email. And take care. See you guys soon. Bye.